Hello, and welcome back to the course on quantum mechanics. So we are now on the fifth chapter for this course, which will be all about identical particles. But before we proceed with the first lesson, let us first discuss let us first review some of the concepts. So in the previous chapters, we have discussed about the wave function, which represents the state of a single particle. So the single particle wave function or the single particle state is given by this linear combination of the time-independent wave functions, which are functions of the position vector. The position vector can be in terms of the Cartesian, spherical, or cylindrical coordinates. And these wave functions or these states actually evolve with time, and their time evolution is given by this Schrödinger equation, where the Hamiltonian is just the kinetic energy operator plus the potential energy operator, and most of the time the potential energy that we consider are time-independent potential energies. So for this lesson, we will be talking about two-particle system. So what happens now to the wave function or to the state of a system if it is now composed of two particles? So suppose you have a two-particle system. So the first particle has mass m1, it has a position of r1. The second particle has a mass m2, it has a position of r2. So you will expect that the wave function will now be a function of both positions, r1 and r2, where both r1 and r2 are assumed to be time dependent. The wave function will now then look similar to the wave function of a single particle, but now it's a linear combination of the time-independent wave function for the two particles with positions r1 and r2. So in this case, the Hamiltonian, which is just the kinetic energy plus potential energy of the system, will now be the kinetic energy of particle 1 plus the kinetic energy of particle 2. So this is the total kinetic energy of the system plus the potential energy. So this could be the potential energy of each of the particles or the interaction potential energy. But this is the total potential energy. So similar with what we had when we discussed about the wave function, we have the Born statistical interpretation. Now, if you now have two particles, say in 3 dimensions, so the absolute value of the wave function squared, this is now a differential volume, d cube r1, differential volume for particle 1, differential volume for particle 2. And this is now interpreted as the probability of finding particle 1 in the volume d cube r1 and particle 2 in the volume d cube r2. So we just expanded our statistical interpretation to 3 dimensions and now to 2 particles. So of course, if you have more than 2 particles, then you just continue the pattern. You will see the pattern that if you now have 3 particles, this will be the probability of finding particle 1 in dV1, particle 2 in dV2, and particle 3 in dV3, and so on. So our time-independent Schrödinger equation will now look like this one. So this is the kinetic energy for particle 1, kinetic energy for particle 2, and the potential energy of the system. So let's now have an example. So example 1 actually has 3 sub-problems. So this is example 1.1. So you have 2 particles, M1 and M2, each with corresponding positions, R1 and R2. So the question now is, for a 2-particle system where R is the separation distance, so this is the separation distance, it's given by R1 minus R2. So recall your vector addition. And R is the center of mass. So if you will recall, center of mass is just summation of M R over the total mass. So you have m1r1 plus m2r2 over m1 plus m2, since we only have 2 particles. If you have 3 particles, then this will be m1r1 plus m2r2 plus m3r3 over the total mass, which is m1 plus m2 plus m3. So R is the center of mass, and mu is what we call the reduced mass. It's m1, m2 over m1 plus m2. Of course, if you have 3 particles, this will become m1, m2, m3 over m1 plus m2 plus m3 over the total mass. So this is the reduced mass. This is actually a correction for the binding energy. Okay. So you need to show that we can actually write R1 in terms of the separation distance and the center of mass. So the capital R is the center of mass, the small r is the separation distance. So you show that you can write R1 and R2 in terms of the new r's, separation distance and the center of mass. So I will do the first one. I will leave the second one to you. So we will start with this one, separation, the center of mass. So if we cross multiply m1 plus m2, the total mass, to r, you will get, so you have r m1 plus m2 is equal to m1 r1 plus m2 r2. So from the definition of the separation distance vector, it's r1 minus r2. Therefore, I can write r2 as r1 minus r. So I can replace r2 here with r1 minus r. So if I do that, I can eliminate r2. And I can now solve for r1. So this is just r minus r1. So I will get something like this. R m1 plus m2, and then m1 r1 plus you will have m1 plus, sorry, this is m2 r1 minus r. Now solve for r1 and you will get r plus m2 over m1 plus m2 r. Now from our definition of the reduced mass, this is just m1 m2, so this is not a vector, over m1 plus m2. So therefore this term here is just the reduced mass, this one, divided by m2. So you can write r1 is equal to the center of mass, capital R, plus the reduced mass, the reduced mass, this term here is the reduced mass over, divided by m1. So divide by m1, so you will get m2 over m1 plus m2, so that one. So mu over m1, which is what we are asked to derive. So this one, r plus mu over m1 r1. Okay. You do the same step for the second item for R2. You do the same for R2. It's actually just a similar step, and you can get R2 is equal to R minus mu over M2 R. That one. So let's now proceed to the second example. Still actually in the same example. So show that the del operators can be written as, in terms of the del operator acting on capital R and del operator acting on the small r, the separation distance, and this is the center of mass. So similarly, similar with the previous problem, I will only do the first one. So we will assume first that the center of mass, the three-dimensional center of mass, is a function of the x center of mass, the y center of mass, and the z center of mass. So the capital R's are the centers of mass for x, y, and z. And the small r, the separation distance r, is a function of the separation distance for the x, the y, and the z. That one. So x, for instance, capital X is just equal to m1 x1 plus m2 x2 over the total mass m1 plus m2. And for instance, the small x, the small separation distance x is just x1 minus x2. So based on our it's still based on our three-dimensional vectors. Okay. Now, the del operator acting on particle 1 is given by partial with respect to x1 I hat, or we'll just use x hat is partial with respect to y1 y hat, is partial with respect to z1 z hat. So that's actually the three-dimensional del operator. Now, if we want to shift from x1 to x2 to capital X and small x, we need to use the chain rule for differentiation. So partial with respect to x1, according to the chain rule of differentiation, this is partial with respect to capital X with respect to x1, partial with respect to capital X, plus partial of small x with respect to x1, partial with respect to small x. So this is the chain rule for differentiation. Now, we have this one, the definitions of the capital X and the small x. So take the derivative of this with respect to x1, and you will get m1 over m1 plus m2. So this value here is m1 over m1 plus m2, partial with respect to capital X, and partial of small x with respect to x1. So with respect to x1, this is just equal to 1. So this is partial with respect to x. Again, this can be written in terms of the reduced mass. This is just basically the reduced mass divided by m2. So mu over m2, partial with respect to capital X, plus partial with respect to x. This is partial with respect to x1. Now, if you do the same for partial respect to y1, this one, and partial respect to z1, you will actually get similar results. So partial respect to y1 will be mu over m2, partial with respect to capital X. No, it's now with respect to y. With respect to capital Y plus partial with respect to small y. And for z, you will have partial with respect to z1 will be mu over m2, partial with respect to capital Z, plus partial with respect to small z. The z separation distance, capital Z, the z center of mass. Now you substitute all of this into this equation and simplify, and you will get you can write the del operator acting on particle 1 as simply mu over m2. They have the same factor, and you group all of the operators with with respect to capital R, and that is basically the del operator acting on capital R plus the del operator acting on R. Take note that this del operator will only act on the center of mass, capital R, and this del operator will only act on the small r, separation distance vector. Okay. So that is what we are trying to do. So you do the same for the del operator acting on R2, and it can be written as this one. So you just do the same steps. Okay. So let's now go to the third example. So the third example is we need to show that the time independent Schrodinger equation can be written as this one. So take note that the original definition of the time independent Schrodinger equation is like this. H acting on psi will be the kinetic energy for particle 1, so 2m1, the del operator, squared, acting on our wave function, the wave function of the system, plus the kinetic energy of particle for particle 2, so h bar squared over 2m2, then the del 2 squared acting on psi, plus the potential energy of the system, so R1, R2, and this is equal to E of psi. So all we need to get is this one, delta 1 squared and delta 2 squared. So we already know it's the definition or its form in terms of the separation distance and the center of mass. So in the previous example, so del 1 squared is actually just del 1 dot del 1 acting on psi. So that is the definition. So del 1 squared acting on psi is just that one. So therefore, del 1 is just mu over m2. We have obtained this result earlier. That with okay, so we will actually have three terms. So the first term will be you have mu over so we have mu over m2 squared, and then del of r, that del of r is just del r squared. And then the second term, so this will be acting on psi. And then you have del of small r, that del of small r, that will give you the Laplacian, del r squared, acting on psi. And then the middle term. So plus 2 mu over m2 del of capital R dot del of small r acting on psi. That one. So you do the same for del 2 squared, just the same, with that with itself, with that the operator with itself. And you will see something like similar to this. You substitute that one to this equation and simplify, and you can obtain this equation. So you will notice that it is something like the kinetic energy for the center of mass and the kinetic energy due to the reduced mass. So something like the kinetic energy for the total mass and the kinetic energy for the reduced mass plus the potential energy. That one. So for our last example, this is with regards to the reduced mass. Oh, sorry. We have this should be example 1.4. So this is example 1.4, still a continuation of the first problem. So show that you can separate the time-independent Schrödinger equation into the center of mass component and the separation distance small r component. So I will leave this one as an exercise for you. So the last example is with regards to the binding energy of hydrogen. So the correct binding energy of the electron in the hydrogen nucleus can be corrected by replacing the electron mass with the reduced mass. So the reduced mass is actually the correction for the mass of the electron when you are calculating the binding energy of hydrogen. So hydrogen has one proton and has one electron. So find the percent error in the binding energy of hydrogen. So the percent error is just the difference between the correct energy by the correct binding energy and the correct and the original binding energy. So in that case, that is the difference between the electron energy, rest mass energy, and the reduced mass energy. So MEC squared minus mu C squared. So it's basically the change in energy. The error in energy is just also the error in mass. To solve for the percent error, by the way, the reduced mass is, since it's a proton and an electron, so it's the mass of the electron times mass of the proton over the total mass. So the percent error will now be theoretical value minus experimental value over the true value. So the true value is the binding energy for the reduced mass. So you substitute that one, C squared will cancel each other out. You substitute mu this, and you will get the percent error is actually just the, it's actually the percent error only depends on the ratio of the mass of the electron over the mass of the proton. So the mass of the electron is this one, it's 10 to the power negative 31. The mass of the proton is actually 10,000 times more massive than an electron. It's 10 to the negative 27. And that ratio will give you approximately 0.054%. Now, if you look at this classically, this is actually a very small error. But take note, in the quantum realm, this is in the quantum realm. So this is actually a very big deal if you don't account for this correction or for this error. So that ends the lesson on two-particle systems. So in the next lesson, we will be focusing now on identical particles. What will happen now if you have particles which you can distinguish from each other and you cannot distinguish from each other if they are identical particles? So in particular, we will be discussing about identical bosons and identical fermions. I will see you again in the next lesson.